Hello everyone, my name is Konala Venkatarama Manohar. Currently, I am pursuing my BTech at Lolly Professional University. Uh, Today, let's delve into the world of data structures and algorithms. Today, we'll be discussing some fundamental concepts of the binary trees, like understanding their structure and exploring the essential operations like the insertion, deletion, and the traversal operations. Like if you're starting out on trees and the binary trees, like this video can be very much helpful to you. So, without further ado, let's go into our topic. So, first of all, what is a tree? Uh, like a tree is a non-linear data structure. Let me do tree is a non-linear data structure. A tree is a non-linear data structure. A tree represents an hierarchical organization, like hierarchical organization. So, like there are many number of trees. Like the a tree is like a basically a non-linear data structure. Like it models an hierarchical organization. Like the advantages of a tree can be uh, we can we can manipulate the hierarchical data and it makes information easier. Sorted lists of data using trees data. So these are the advantages of tree, and that is a brief introduction to trees. So there are basically three types of trees, three major types of trees. One is the binary tree, another one is the binary search tree, and the third one is the complete binary tree. So so the by the word itself, we can tell that binary tree is something that has two, right? So what basically that two define? So like every tree has a node, a leaf node. So a node, or so the first node of a tree is known as the root node of a tree is called root node. So that is something called as a root node. So in a binary tree, every node has sorry. So let us see how a tree can be represented. So, So like this is how a tree can be. So like let's insert some values. 3, 4, 5, 6, and 7. So for our convenience, let's take this. So this is how a binary tree can be. A binary tree has at most uh, at most two nodes. So right now, what you're seeing is a binary tree. So even if we take this node out, this is still a binary tree. Has it has like an at most of two nodes means that there can be zero, there can be one node or two nodes. At most is like that is the maximum number of nodes a node can have in a binary tree. So what is a binary search tree then? So binary search tree is like a special case. So we can call this BST. So in which the left child has a value less than the parent, and the right child has a value greater than the parent. So this right here can be called as a BST because just see that uh, here the parent node right here one is less than the left node here. So okay, maybe we can change the values a little bit. So this can be turned into BST. So let's look at our conditions like the left child has a value less than the parent child, right? So maybe let's take this as 4. So and this has some 3. So the right child should have a value greater than the parent. So let this be 5. So same goes here. This should be less than the parent right here. So let us take it as some 2, and the right child is already greater than the parent. So here the 3. So here already the right child is greater than the parent child. So let's take some another value right here. So let's let it be 1. So like this right here is a binary search tree. Like the root node here is is greater than the left child and less than the right child. And same for the 5 and same for the 3. Let's take some another value. Let it be 8. So this is an BST. So a what is a CBT? That is a complete binary tree. So then let us go to the third third complete binary tree. That is the complete binary tree. So how is complete binary tree different than the other two? Let it be CBT. So a complete binary tree has all like it is the type of binary tree where all levels of the trees are filled completely except the leaf nodes. So what is a leaf node now? Uh, what is a leaf node? A leaf node is a node without any children. Means there is no successor for that node. So uh, right now here we can take the 2 and 7 as leaf nodes because they don't have any children, and there is no successor for 2 or 7 right here, right? So this right here can be a complete binary tree, has every tree is filled, and there is no like this can be called as a complete binary tree because every tree is here is filled. So this is the left subtree right here, and this is the right subtree right here. Both are filled, and the leaf nodes are not need to be filled. So this is what a complete binary tree is. So moving on to the next topic, let's discuss some terminologies. As I said earlier, a root node is the first node of a tree. This is the root node, and 7, 2, 8, and 1 right here are called as leaf nodes. Means the node without any children and no successor for it. So what is an edge? So this right here can be called as an edge. Edge is something like uh, an edge is an edge is an link between two nodes. So this right here can be called as an edge between 4 and 5, and between 5 and 2 right here, between 5 and 7 right here. These are also called as an edges. This is called an edge. So what can be the maximum number of edges in a tree, right? So like number of edges in a tree can be n minus 1, where n is number of nodes. So let's suppose that there are 1, 2, 3, 6 nodes here, and the edges are 5. So the maximum number of edges right here are 5. So that's obvious. So what is the height of a tree? So like the number of edges from leaf to that node. So let's take that. Let's take the height of 3 here. So how many edges are there for 3 from the leaf node? That is 8, right? So only one edge. So that is one edge from here and one edge from here. So the height here is 3. Height here is 2, okay? So height of a tree can be the height of this root node from the leaf node in the longest distance possible. So that is 2. So height of this tree will be 2. So in the same way, what is the depth of a tree? Sorry. So depth of a tree is the number of edges from root to that node. So like if you want to see the depth of 8, so that will be number of edges from 4 to 8. That will be from here to here. So that will be 1, 2. So that will be 2. So the depth of 8 here is 2. So depth of a root node. So what is the depth of a root node? So the depth of a root node is always 0 because we can't we can possibly we could possibly have any number of edges from the root to itself. So the depth of a root node is always 0. Depth of root node is 0. So same way the height of a leaf node is 0. Of a leaf node is 0. So these are some basic terminologies of the tree, and these are the types of trees. So a binary tree can be traveled using 3 ways. That means a binary tree can be traveled. A binary tree can be traveled using using three ways. One is the pre-order, another is the post order, and the last is the in order traversal. So what are these post, pre, and in order traversal? Let's see them. Let's start with the pre-order. In the pre-order traversal, we travel in the binary tree. Uh, like uh, let's suppose that let's take a binary tree here. Let's take this binary tree as an example. So in the pre-order traversal, we first visit the root node. The root node is first visited, then the left node is visited, and finally the right node is visited. Okay, so for our convenience, let's take a simple binary tree. Let it be A, so let it be B, let it be, so let it be C, let this be D, let this be E, and let this be F, and let this be G. So, so for this binary tree, let's traverse using pre-order. So traverse basically means traverse means like visiting every node. So right now we are discussing pre-order. So the condition in the pre-order is that the root node is first visited. So let's start with the root node itself. So that means our root node will be the first. So after the root node, we have to visit the left node. So the left node here is B. So so we have to go to B now. So we have visited B now. So again at B, so B is a subtree of A right here. So again we have to use pre-order here. So that would be the root node is visited, then we have to go with the left node. So that is D. Sorry. So that is D right here. So in the A, so that is the initial root node. We have visited B, that is the left node of A. So at B there is another subtree. So BD is another subtree in A. So we have to apply pre-order again. So right now we have visited D. So and now we have to go with the right node. So that is E. So that is E. So right now at instance we have completed the left node totally. We have first visited the root node that is A. Then we have went with the left node that is B. So in the B again we have implemented the pre-order. So right now so the left node is completed totally. Let's go with the right node now. So so when we are visiting the right node here, so now we have to start with C. So right now the root node here is visited, the left node is visited. So the according to the pre-order, so we have to visit the right node now. So that would be C here. So at C again we have to implement the pre-order, right? So we will visit F, then we will visit G. So like this is how we visit every node using pre-order now. So so we will visit first we will start with the root node, then we will go with the left node, then we will append pre-order again. Then we will go to the right node here, then we are going to upgrade pre-node here. So that would be A, B, D, E, C and F, G. So now let's go for the post order, post order traversal. So in the post order traversal, okay, I forgot a point here. So from the name itself, we can tell that. So the name is pre-order, right? Pre means first. So the root node is first visited. So hence the name pre-order. So just by the name we can tell that in the post order also it's going to be something same. So post order means after, right? So in the post order, the root node is visited last, is visited last. Uh, left node is visited first, and the right node is visited next, right after the left node is visited. So basically, this follows the order that is left, right, and root, and the pre follows the order root, left, and right. So like for the above binary tree, let us apply the post order and see the result. So in the post order, first the left node is visited, so that would be B, right? So B right here is a root node. So again at B we have to again apply the post order conditions. So at B again, so at B as B is again a subtree, we have to go with D. So that is the left node of B, right? So applying post order at D at B subtree. So that would be first we will visit the D node here. Then we will go to the right node. So that is E. So that would be E. So at last we will visit the root node of the B subtree. So that is B. So as of now, the left node is visited first in this whole BDE subtree. So as B is the left node of A, so according to the post order conditions, we will now go with the CFG. So okay, when we visit C here right here, so we have to visit the left node first. So then we will go with F right here. So again, after the left node is visited, we will visit the G. We are have to visit the right node here. Okay, so that would be G. So after visiting the left node and the right node, at last we will visit the root node. The root node of this subtree is C. So now the both subtrees are traversed, means the root node's left child and the right child are now traversed. So according to the condition, we will now traverse to the root node. So that is A. So using post order traverse method, this is how we traverse uh, in this tree. So we will start with D here, then go to the right child, then go to the root node of this subtree. So right as of now, the left side of this node is completed. So now we will go to the right child. So that is CFG, right? So in the CFG again, this is a tree. We will have to use the post order. We will visit the left node, then we will go to the right node, then we will visit again the root node. So as the even the post order we are traversed to this tree also. So now we will go with this root node. So that is A. So this is all about the post order. So now let's see the in order also. So uh, unlike the post order or the pre-order, in order, uh, the left node is visited first again. Left node is visited first. So then root node is visited. So at last, after visiting the left node and the root node, the leftover right node is visited. So this follows L root R. So let's implement in order for this binary tree right here. So the condition is that, we have to visit the left node first. So again here BDE is a subtree as itself, right? So first we will go with D here. We will start with D. Then we will go with the root node. So that is B. Then we will go with the right node that is visited the last. So that is E. So as of now root for the root node right here A, the left node is traverse. So now we will go with A. So now the as of the condition the root node is visited, sorry, the left node is visited, then the root node is visited, and then we have to visit the right node. So in the right node again this is a subtree itself. So we will have to visit the left node first. So that is F. After visiting F we will visit the root node again. So that is C. So after visiting C then we will go with G. C, G. So this is the condition for in order. So this is how we traverse in order. First we will traverse starting from the left node, then we will visit the root node, then we will go with the right node. So this is all about the traversing methods and all. So now let's implement the coding part. Let's implement it practically. So let's start with the insertion part. So let's see how to insert a new node to a binary tree. So for that, let's create a node class. Def init self comma, let val be some value that we are going to take. So self dot none, right? None. Self dot val is equals to, oh sorry, so let this be some key. So self key. So right now what we have done is that so this class right here defines the structure of a node in the BST, like the binary search tree in which we are going to insert a node. So each node has three values: the left, right, and the val. The left and the right here will be pointing to the left and right child respectively, and the value stores the key value of that node. So now let's define a function. So that will be def insert root comma key, root comma key. So if root return node return node key, else if root dot val is less than key. So that means root dot is equals to insert root dot right comma key. else root dot left is equals to insert root dot left comma key. Setting generation return root. So like this function recursively inserts a new node within the given key. Like if the BST, if the binary search tree is empty, like if the root is empty, a new node is created and returned as the root. Otherwise, the function compares the key. Otherwise, the function compares the key with the root. Otherwise, the function compares the key with the value of the current root node. Like if the key is greater than the value, then the function recursively calls within itself, and it adds and calls itself with the right root dot right as the new node. If the key value is less than or equals to the root dot val, then the function itself calls with root dot left as the new root. So this ensures that the new root is inserted into the left subtree. So this is how we insert in a binary search tree. So let's check how to delete in a binary search tree. So let's create another class here. Define self. Okay, so let self dot left self dot key is equals to key and self dot right is equals to none, and self dot left is equals to none. So unlike inserting, deleting is kind of a tricky process. So like we can break down delete into three scenarios. Three scenarios. Like the first can be uh, if the value as at the is at the leaf node. So if the value is at the leaf node, then we can assign that node value to null. So hence deleting is easily node value to null. And so if there is a how if the second scenario can be like delete a single delete a node. Okay, let it be delete a node with single child. So like if there is only if there is only a single child, like let's take this let's take this as an example. Let's suppose that there is no f right here. So if we have to delete c, like we have to delete c node from this binary tree. So then we can just copy the child node of this C to the node, and then we can delete C. So as we did for the leaf node, we can do the same thing, as we can just change values for the G and C. We can copy the child to the node and then delete node. So let's go with the third scenario. So that is nothing but uh, delete a node with two children. This is not simple as the previous ones, because we can just we can assign the node value to null, or we can just swap the child and the node. This is not simple as the previous ones. We have to uh, we have to delete it, so that the BST properties are not disturbed. So so that we can just take so the logic is to find the in order successor of that node, and then swap it. So for better understanding of this, okay, let's go here. Let's take a node here. Let it be some h. So if you want to delete the root node A here, so A right here has two nodes, right? So it is a node with two children. So first we have to see the in order successor. So in the in order successor of the A will be H here, right? So swapping A with H, so that so then the root node becomes here A, and then here H becomes here, right? So here A is the leaf node again. So we can just delete A here. So this is how we implement using the both children, and the if a node has two children and one children, or if it is a leaf node. So now let's implement it. So let us take another class, binary tree. And init. So let self dot root is equals to none. So like let us use the insert function which we did previously. Like if there is an empty if the binary tree is empty. So let's use this. So let's change the class names. Node. So here instead of root we have to change it again to node as we have taken node here. So if node is none, return node comma key. So that is node key. So this is again we have to change it here. No dot right. Okay, so now let's get the in order function also as we need it if there is a if you have to delete a node with two functions. So that is there in order self comma root. So if root self dot in order root dot left, mm, print key self dot in order is root dot right. So as we discussed earlier in the in order function, uh, like apart from the other, the in order function in order function we will first visit the left node, the left root here, then we will visit the right node, and no, then we will visit the root node here, then we will visit the right node at last. So that's what has happened here. So here we have also defined the in order function. So let us so delete node self comma root comma key. So if root and so let it return the root itself because there is nothing to delete. If key is less than root dot key, then root dot left is equals to self dot delete node. So root dot left comma key. So right now what we have done is that if the root is none, so it is gonna return root, or else if the key value, like if the key to be deleted is smaller than the root's key, then it would be lie in the left subtree. So then we would go with the left subtree. So now, the same condition, but the condition, let's take another case, that is if the key value is greater than the, so let's change this. So if that is greater, then it would transverse left side, right side, sorry. So here what we are doing is, the key to be deleted is greater than the roots key, then it lies in the right subtree. Okay, so that is for the key to be deleted. So uh, let's take another condition where if the node has, so let's try it here, node with only one child or no child. Sorry for that trouble. So if row dot left is none, then return row dot right. Elif row dot right is none. Sorry, this is then uh, return row dot left. So let's see, like, so this is for node with only one child or no child. If there is only one child, then as we said, if the root of the left, like the left pointer is none, then it is going to return the right child. Okay, so let's say if node with two children. So right now we have, so uh, what to do if the node has two children, right? So we have, as we discussed earlier, get the in order successor. So that will be the smallest in the right subtree. So the root dot key is equals to self dot min value. So for this min value, we have again defined a function min value here. So min v is equals to root dot key. If the root dot left, like while root dot left, like taking the value from the smallest in the trie subtree, min v is equals to root dot left dot key, then we are assigning the root is equals to root dot left, and then this is the driver code right here. So let us create this following bst right here. So we are inserting the values 50, 30, 20, 40, 60, and 80. So let's so for so if we have to delete the node left 20 right here, let's run this. Okay, there is a problem. So that is all about deleting and all. So now let's go with the transversing methods. So let's start with the pre-order. So, so it wrote print root dot val, come on, and is equals to I forgot to initialize a class right now. So I took a class with the self rod left, which is pointing to the left cell, and right to the right cell, and value to the key value that we are going to give. So, and now for the pre-order, so if root, first we will start with the root value, that is the key. Then we will, so now let's, in the pre-order transversal conditions are going with the root, then the left, then the right, right? So now we have went with the root. Now let's go with the pre-order traversal. So root dot left, then the last will be the pre-order right. So now what is happening here is that uh, by this we are traversing through the left subtree, means we are recursively traversing the left node here, and in the by the pre-order traversal root dot right, we are traversing recursively through the right subtree. So now let's take some example values. So that can be root is equals to, so let root be node 1, root dot right is equals to node of 2, root dot left, sorry, left is equals to node of 3. So let's call the function, that is pre-order traversal. Looks like there is an error. So this is the code for the pre-order traversal. The function takes root node as the input. If the root node is not none, it prints the value of the root node, and then it recursively calls itself within the right and the left. Oh, sorry. So now let's go with the post order. Again, let's take a class such as this. So let's define, sorry, that is post order, right? Post order traversal. So if the root is not none, so that is if root. Oh, so this is post order, right? So post order means the root comes last. So that would be post order traversal root dot. After it visits the left node, we have to visit to the right node. So that is root dot right. So after going for the left and right, so post means last rate. So then we will print the value of the root node. So the function here it recursively goes itself through the left child and the right child, and then prints the value of the root node if there is any value. So this is all about the binary trees and the types of binary tree and the traversal methods like the post, pre, and in order methods. So I would like to thank myself for giving me this opportunity. Thank you.